Module 2, Lecture B, Features and Splits. By the end of this lecture, you will be able to extract practical features from tabular, temporal, and image-style mechanical engineering data, implement manual train and test splitting without using machine learning libraries, and scale numerical features and explain why scaling affects distance-based and gradient-based models. Mechanical feature extraction, practical feature basics. Raw engineering data often needs to be transformed before it is useful for analysis. Practical features should capture the system's physical behavior, not just add more columns. For example, average motor current over a cycle, or the difference between loaded and idle current, can be more meaningful than a single current reading. Good features connect data to concepts like load, speed, and temperature, helping reveal patterns and improve predictions. Mechanical data tables become useful when raw measurements are cleaned and turned into meaningful features. Values such as pressures, flow rates, or manufacturing signals can be summarized into indicators of operating state, machining regime, or process stability. Careful handling of units, missing data, and labels is essential so the resulting features support accurate and reliable analysis. Practical features turn raw data into useful information for comparison and analysis. An engineer might track how a bearing's temperature differs from the surroundings, how quickly it heats up, or how load and speed affect it. In other cases, useful features might include suspension displacement, average load, or image properties such as area, shape, and brightness. Python code. Practical feature basics. Practical features turn raw measurements into useful summaries. In mechanical settings, these may include tables, signals, or small image grids that capture important patterns, such as defects. The script imports 3 core Python libraries for data work. NumPy supports efficient numerical calculations. Pandas helps manage and analyze tabular data, and matplotlib pyplot is used to create visualizations. Together, these tools prepare the script for data processing, analysis, and plotting. We create a small pandas dataset to represent pump test measurements. It includes 4 observations of inlet pressure, outlet pressure, flow rate, and rotational speed under different test conditions or time points. Organizing the data this way makes it easy to analyze and manipulate using pandas. The pump dataset is enhanced by adding 3 physically meaningful features. Pressure rise is found by comparing outlet and inlet pressure. Flow rate is converted from liters per minute to a normalized liters per second measure. And pump speed is grouped into low, medium, and high bands using the pandas cut function. These added features make the data easier to interpret and more useful for analysis or modeling. A 1-second time range is created with 100 evenly spaced points to represent the vibration signal. The signal combines 2 sine waves, a stronger 12 Hz component and a smaller 36 Hz component. Together, they form a more realistic vibration pattern with multiple frequencies. We summarize the vibration signal using 3 key measures: its root mean square for overall energy, its maximum absolute value for peak intensity, and the number of times it exceeds 0.35 to identify significant vibration events. We create a small 5x5 temperature grid to represent a thermal image. Each value is a temperature in degrees Celsius, with cooler edges around 32 to 34 degrees and a hotter center reaching 78 degrees. This simple pattern helps show temperature variation and makes it possible to identify hot spots. To analyze hot spots in a thermal image, first mark every grid value above 50 degrees as hot. Then count those hot pixels, find the highest temperature, and calculate the average temperature across the grid. Together, these measures show both how widespread the hot spots are and how intense the heat is. We validate the data by checking that each structure has the expected dimensions. The pump data should have 4 rows and 7 columns. The vibration signal should align with the time array. And the thermal image should be a 5 by 5 grid. These checks help catch data structure problems early. The output checks the newly added pump data features and summarizes key sensor results. It reports the final pump's pressure rise, vibration statistics including root mean square, peak value, and threshold exceedances, and thermal image measures such as hot pixel count, maximum temperature, and average temperature. This plotting sequence creates a small figure to display thermal image data using the Inferno color map. A color bar labeled temperature C explains how the colors relate to temperature, and the plot is given the title Thermal Feature Example. The layout is tightened so everything fits cleanly, then the image is shown for visual inspection. This script shows how to extract useful features from mechanical and thermal data. It builds a small pump dataset with derived measures such as pressure rise, flow fraction, and speed category, then analyzes a synthetic vibration signal using root mean square, peak values, and threshold exceedances. It also examines a thermal image grid to identify hot spots and summarize maximum and average temperatures, then displays the temperature pattern with a color map. Signal features. Signal features are compact measurements taken from changing data, such as vibration or temperature. In mechanical engineering, they turn raw signals into useful values like average levels or peaks, making it easier to compare machines and conditions. Their purpose is to keep the information needed to answer engineering questions, such as whether a bearing is wearing out or a compressor is malfunctioning. Signal features summarize how a signal behaves within a chosen time window. The mean shows the typical level. Maximum and minimum values capture extremes, and standard deviation reflects variability or stability. In vibration analysis, energy and intensity features help reveal problems such as imbalance or damage. The window length matters because it determines whether the features emphasize rapid changes or more steady behavior. Signal features summarize the shape, rhythm, and frequency content of machine data, helping reveal normal behavior and possible faults. Measures such as dominant frequencies, spectral energy, and peak-to-average ratios can show rotation patterns, gear or bearing issues, impacts, and shocks. Good feature extraction depends on understanding the sensor, the machine, and the operating context, making these features useful for comparison, diagnosis, and control. Python code. Signal features. Signal features condense changing sensor measurements into useful summaries. By analyzing small time windows, they help reveal practical machine behavior, while built-in calculations support engineering interpretation. The script begins by importing the main tools needed for signal processing and analysis. The math and statistics libraries provide basic mathematical and statistical functions, while NumPy supports numerical calculations and array operations. Matplotlib's plotting tools are included to create visualizations of the data. To generate a consistent vibration signal, the random seed is set to 7, so the same random values are produced each time. The signal is sampled at 200 Hz for 2 seconds, giving a total of 400 samples. This defines the basic time series setup for the vibration data. The sensor time values are created by converting sample counts into seconds using the sample rate. A 12 Hz rotation frequency is then used to generate a sine wave, producing a periodic vibration signal with an amplitude of 0.35. A realistic vibration signal is created by combining three parts: a base signal, small random noise, and a brief impact event. The noise represents normal random fluctuations, while the impact is modeled as a short, sharp spike in the data. Together, these components simulate vibration data affected by both background variation and a distinct sudden impact. Before feature extraction, the code validates the vibration signal to ensure the data is reliable. It checks that the signal has the expected number of samples, that the sample rate is positive, and that all signal values are finite. These checks help confirm the data is complete, valid, and safe for further analysis. We summarize the vibration signal using 4 key measures. The mean gives its average level over time, while the standard deviation shows how much the signal varies around that average. The root mean square captures the signal's overall magnitude or power, and the peak value identifies the largest absolute amplitude, which helps detect extreme events or impacts. The signal is first centered by subtracting its average value, so the analysis focuses on fluctuations around the central level. The code then detects zero crossings by finding where neighboring values change sign. Counting these crossings gives a simple feature that describes how often the vibration signal passes through its center. To estimate a signal's dominant frequency, compute the frequency bins from the sample count and sample rate. Then apply the real fast Fourier transform to the mean-centered vibration signal. The resulting spectrum shows the strength of each frequency component. By ignoring the DC component and selecting the largest remaining spectrum value, we identify the frequency with the highest amplitude as the dominant frequency. The calculated signal features are stored in a dictionary, so they are easy to organize and retrieve. Descriptive keys identify values such as the mean, standard deviation, root mean square, peak value, zero crossings, and dominant frequency. The dominant frequency is converted to a consistent numeric type, making the feature set ready for later analysis or reporting. The output begins with a header that identifies the summary of pump vibration signal features. It then goes through each feature and prints its name with a neatly rounded value. This creates a clear, compact display of the extracted features, so the results are easy to read and interpret. This plot shows a vibration signal over time and adds a dashed horizontal line for the signal's mean value, making it easy to see how the acceleration fluctuates around its average. The axes label time in seconds and acceleration in g, while the title and legend clarify the purpose of the visualization. The layout is adjusted neatly before displaying the figure. This script creates a 2-second synthetic pump vibration signal by combining a sinusoidal pattern, random noise, and a short impact event. It then extracts key time domain features, including average level, variation, overall energy, peak value, and zero crossings, and uses a Fourier transform to estimate the dominant frequency. The results summarize the signal's behavior, while a time plot with the mean level helps show the noise and impact in context. Derived features. Derived features turn raw engineering data into more meaningful measures that help explain system behavior and improve model learning. For example, pressures, flow rates, dimensions, or cycle times can be transformed into indicators such as operating changes, deviations, or production rates. The key is to use engineering insight to create features that are relevant, useful in operation, and helpful for diagnosis. Derived features combine raw measurements to reveal useful patterns, such as differences, ratios, rates, and normalized values. In mechanical systems, these can show effects like temperature change, pressure drop, load per area, or energy use per output. Time-based features, such as change rates or time since maintenance, help connect data to physical behavior like wear, efficiency, and system performance. For image-based engineering data, such as thermal or inspection images, useful features turn visual patterns into structured measurements, like the size of a hot region or the average temperature in an area. These features should be grounded in domain knowledge, calculated consistently, and based only on information available at prediction time. Otherwise, noise or future data can create misleadingly strong model performance. Python code, derived features. Derived features help connect raw measurements to the underlying mechanics. Simple examples make these engineering transformations easier to understand, while built-in tools keep the feature logic clear and transparent. The code imports the math library for advanced mathematical functions and constants. It also imports the statistics library using the shorter name stats, making it easier to call statistical tools for analyzing data, such as calculating averages. A dictionary is created to store key measurements from a small pump test. It records the inlet pressure as 120 kilopascals, the outlet pressure as 355 kilopascals, the flow rate as 48 liters per minute, and the speed as 1,750 revolutions per minute. Organizing the data this way makes the measurements easy to access and use in later analysis. To evaluate pump performance, calculate the pressure rise as the outlet pressure minus the inlet pressure. Then find the normalized flow by dividing the flow rate by the pump speed. Together, these values show how much pressure the pump adds and how efficiently it moves fluid relative to its operating speed. A dictionary is used to store key measurements for a manufactured part, making the data easy to access for later analysis. It includes the part's actual length of 4.02 inches, target length of 4 inches, mass of 185 grams, and production cycle time of 32 seconds. Length error is found by comparing the actual part length with the target length to measure the deviation. Production rate is found by dividing the number of seconds in an hour by the cycle time, giving the number of parts produced per hour and indicating manufacturing efficiency. A short temperature history is stored using time points in seconds and matching temperature readings in degrees Celsius. Together, these paired values show how temperature changes over time and can support simple time-based analysis, such as estimating the rate of change. Before calculating a rate of change, confirm that the time points and temperature measurements match in number, so each time has a corresponding temperature. Also, make sure there are at least 2 time points, since a rate requires both a starting and ending value. To find the average warm-up rate, compare the first and last measurements. Subtract the starting time from the ending time, and subtract the starting temperature from the ending temperature. Then divide the temperature change by the time change to get the temperature increase per second. We define a small grid of temperature readings to represent a thermal image. The grid is arranged in rows, with each value showing a temperature in degrees Celsius for a specific area. This structure makes the data easy to analyze, such as finding hotspots or comparing temperature differences. The code turns a 2-dimensional thermal image into one flat list of temperature values. It then selects the values that are at least 55 degrees, treating them as hot pixels for further analysis. To analyze the thermal image, count the pixels at or above 55 degrees to identify the hot areas. Then find the average temperature of those hot pixels and compare it with the average temperature of all pixels in the image. The difference between these two averages gives the thermal contrast, showing how much hotter the hot regions are than the image overall. The output presents a compact summary of derived mechanical and thermal features. It reports pump pressure rise, flow per speed, part length error, production rate, warm-up rate, hot pixel area, and thermal contrast. Together, these values describe key performance, dimensional, production, and temperature characteristics from the data. This script turns mechanical and thermal measurements into useful performance indicators. It evaluates pump efficiency through pressure rise and flow per speed, checks manufacturing precision and output using length error and production rate, and measures how quickly the system warms up. It also examines a thermal image to find hot areas and estimate thermal contrast, then prints the results to summarize mechanical performance and thermal behavior. Manual data splitting. Split strategy. A split strategy decides which data trains a model and which data tests it, so performance reflects how the model will handle unseen cases. This matters because engineering data can contain hidden patterns, such as repeated tests or time sequences, that may make results look better than they really are. The split should match the intended use, test on unseen pumps when predicting new pumps, or on later data when forecasting the future. The goal is to make testing resemble the real decisions the model will support. For independent tabular data, a careful random train test split can give a useful performance estimate. But if the data includes repeated measurements, image patches, or related samples, split by groups such as component or batch so the test set contains truly distinct cases. When outcomes are rare, also make sure both training and testing sets include meaningful examples to avoid misleading results. When splitting data, match the split to how the model will be used in the real world. For time-based data, train on earlier records and test on later ones to avoid future information leaking into training. For image data, keep all images of the same item in the same split so the model learns general patterns rather than memorizing identities. Document the split strategy and its assumptions so others can judge the model's real-world reliability. Python code. Split strategy. Manual splitting helps ensure honest model evaluation when engineering rows contain hidden group relationships. This example contrasts two splitting strategies to show why the choice of split can affect how reliably a model is assessed. The script begins by importing the tools needed for data generation and analysis. The random library adds variability by generating random numbers, while pandas provides data structures for working with tabular data. Together, these imports prepare the code to create and manipulate realistic data. First, the random number generator is given a fixed seed, so random results stay the same each time the code runs, supporting reproducibility. Then, an empty list is created to hold the repeated measurement data from several pumps. The process generates simulated pump readings for 6 pumps over 4 minutes. For each pump, it creates observations with a pump label, minute, vibration level, and temperature, using small random changes to make the values realistic. Vibration is based on the pump ID, while temperature increases with the pump ID and also vary slightly. Pumps with IDs 5 and 6 are marked as needing service, and all observations are collected into a list. We use pandas to create a data frame that organizes the generated pump measurements into a structured table. We then check that it contains 24 rows, confirming that all expected data was captured correctly during preparation. For random row splitting, the code gathers the row positions from the data and shuffles them to create a random order before splitting. This helps randomize the training and testing sets, but it can also place rows from the same pump in both sets. As a result, the model may learn information tied to pump identity, causing potential data leakage. To create an 80-20 data split, first choose the point that marks 80% of the dataset. Rows before that point become the training set, and the remaining rows become the testing set. This gives most of the data to training, while keeping a smaller portion for evaluating model performance. We first collect and sort the unique pump identifiers to create a consistent order. Then we randomly shuffle the pumps so the data can be split while keeping all observations from each pump together. This preserves the grouped structure when forming training and testing sets. To create a clean test set, reserve the last two shuffled pump identifiers and include only data from those pumps in testing. The training set is then built by excluding those same pumps. This keeps pump identifiers from overlapping between training and testing, so the evaluation measures performance on entirely separate pumps. We compare the training and testing sets to see whether the same pumps appear in both. This is checked for both random row splitting and group splitting by looking for shared pump identifiers. The amount of overlap shows how well each split keeps the data separated and supports a fair evaluation. This section demonstrates two ways to split the dataset for model evaluation. It first reports the dataset size and number of unique pumps, then compares a random row split with a group split that keeps pumps separate. The random split may place the same pumps in both training and testing, creating possible data leakage, while the group split checks that no pumps overlap and identifies which pumps are held out for testing. The key takeaway is to choose the split strategy that best matches future engineering use, so evaluation results are reliable. This script compares two ways to split pump measurement data for model evaluation. A random row split can place measurements from the same pump in both training and test sets, which may make performance look better than it really is. A group-based split keeps each pump entirely in one set, holding out some pumps for testing with no shared pump identifiers. This is better when the goal is to test how well the model works on pumps it has never seen before. Train, test, split. Splitting data into training and test sets helps check whether a model can work on new, unseen data. The training set teaches the model patterns, while the test set evaluates how well those patterns generalize. If performance is strong on training data, but weak on test data, the model may be overfitting by memorizing instead of learning useful relationships. When splitting data into training and test sets, use a controlled, reproducible proportion, with most data used for training. Random splitting is appropriate when rows are independent, but the test set should still reflect important structure in the data, including rare outcomes and different sources such as machines or sites. A balanced test set gives a more realistic measure of model performance and helps avoid misleading results. When splitting data manually, make sure the split matches how the data will be used in practice. For time-based data, train on earlier records and test on later ones. And for group data, keep each group together. Clearly record the split rules and proportions, so the evaluation is realistic and reproducible. Python code, train test split. Manual data splitting helps ensure a fair evaluation of a model. In this example, the data comes from pump vibration records, and the process can be done without using machine learning libraries. We import the random library to shuffle data in a reproducible way, and pandas to manage the dataset as a data frame. Together, these tools prepare the data for efficient organization and processing. We create a small, simulated engineering dataset where each record represents one pump. Each pump entry includes an identifier, vibration level, temperature, and a failure indicator, with 0 meaning no failure and 1 meaning failure. This simple structure is useful for testing with data that resembles real pump monitoring records. This dataset sample contains 3 pump records, each with a pump ID, vibration level, temperature, and failure status. Pumps P04 and P06 show lower vibration and temperature readings with no failure, while pump P05 has higher readings and is marked as failed. These records help support pump performance evaluation and failure prediction. This dataset defines 3 pump records, each with an identifier, vibration level, temperature, and failure status. The dataset includes 3 pump records with vibration, temperature, and failure status. Pumps P10 and P11 show lower vibration and temperature readings and have not failed, while pump P12 has higher readings and is marked as failed. These records help analyze how vibration and temperature relate to pump performance and failure rates. We first use pandas to turn the list of records into a data frame, which organizes the data into rows and columns. Each record becomes a row, and its fields become column headers. This tabular structure makes the data easier to process for later steps like shuffling and splitting into training and test sets. Set the random seed to 42, so the shuffle is reproducible each time the code runs. Then, create a list of row positions, shuffle that list, and use it to rearrange the data frame rows. This mixes the data consistently before splitting it into training and test sets. The training set size is set to 80% of the available data, leaving the remaining portion for testing. A validation check then confirms that this size is greater than 0 and smaller than the full dataset, preventing an empty or invalid split. The shuffled indices are split into 2 non-overlapping groups, the first 80% for training and the remaining 20% for testing. This keeps the training and test data separate, which is essential for evaluating the model fairly. We create separate training and test datasets by selecting rows from the original data using shuffled indices. After each selection, the index is reset, so the new data frames have clean, zero-base numbering. This split lets us train the model on one random subset and evaluate it on unseen data. We collect the pump identifiers from both the training and test data, then check that the 2 groups do not overlap. This confirms that no pump appears in both sets, helping preserve a clean and valid data split. The output confirms that the pump records were manually split into training and test sets. It reports the total number of rows, then shows how many rows are used for training and how many are reserved for testing. This provides a quick check that the split was performed correctly and that the data is distributed as expected. We compare the average pump failure rate in the training and test data by taking the mean of the failure indicator in each set. Printing both rates to 2 decimal places makes it easy to check whether failures are similarly balanced across the 2 splits. This helps ensure the test set provides a fair basis for evaluating the model. The code displays which pump identifiers are in the test dataset by collecting them, sorting them, and printing the result. This confirms which pumps are reserved for testing and helps ensure they are not included in training. This script creates a reproducible train test split for pump vibration data, using 80% of the records for training and 20% for testing. It shuffles the data, verifies that no pump appears in both sets, and reports the row counts for each split. It also compares failure rates between the training and test sets and lists the pump IDs held out for evaluation. Leakage prevention. Preventing data leakage is essential when splitting data into training and test sets. Leakage occurs when test data or future information influences training, making a model appear more accurate than it will be in real use. For example, a failure prediction model should not use information only available after the failure. Even subtle steps, such as calculating summary statistics before the split, can contaminate the test set and make it no longer represent truly unseen data. To avoid data leakage, keep the test set separate after splitting the data. Any pre-processing decisions, such as scaling, outlier handling, missing value imputation, or image adjustments, should be learned only from the training data. This prevents information from the test set from influencing the model and producing overly optimistic evaluation results. To prevent data leakage, split data in ways that respect how records are related. Random splits can be misleading when rows come from the same machine, batch, or time sequence, because the model may learn patterns it would not know in real use. Instead, separate data by logical groups or time periods so the test set reflects real-world conditions and gives a more reliable measure of performance. Python code. Leakage prevention. Show a small, clear example of how data leakage can happen when splitting data manually. After the split, use only statistics computed from the training data, so information from the test data does not influence the model. The code imports the random library to generate random numbers, which supports tasks involving randomness. It also imports the statistics library to calculate measures like the mean and standard deviation, helping summarize and analyze data distributions. First, a fixed random seed is set, so random operations give the same results each time, supporting reproducibility. Then, an empty records list is created to hold the simulated pump sensor readings generated later. This creates a small simulated dataset for 12 pump sensors. Each pump is assigned an ID, a temperature based on that ID, and a vibration level based on the temperature plus a small random noise value. The ID, temperature, and vibration reading are stored together for later analysis. The records are first shuffled, so their original order does not influence the split. The data is then divided at the 75% point, using the first portion for training and the remaining portion for testing. This gives the model most of the data to learn from, while keeping a separate set for evaluating its performance. The code first confirms that the training data has enough rows and that the test data is not empty. It then separates the temperature values from each set into their own lists. This prepares the data for later calculations while helping prevent data leakage. The code combines temperature values from the training and test sets before calculating the mean and standard deviation. This creates data leakage because the pre-processing uses information from the test set, which should remain unseen during training. As a result, the model evaluation may no longer be fair or reliable. We compute the mean and standard deviation using only the training temperatures, so pre-processing does not leak information from other data. We also check that both the safe and leaky standard deviations are greater than 0, confirming the data has variability and the calculations are valid. To illustrate data leakage in scaling, We compare two ways of transforming the first temperature value from the test set. The leaky scaler uses statistics from both training and test data, so the test set influences the preprocessing. The safe scaler uses only training data statistics, which is the correct approach because it keeps test data separate and prevents leakage. The output compares a leaky preprocessing approach with a safe one. It first checks the training and test set sizes, then shows that using all data to compute scaling statistics lets test data influence the process. The safe approach computes the mean and standard deviation only from the training data, then applies them to the test value. The key rule is to split the data before preprocessing so the test set remains truly unseen. This script shows how data leakage can happen during preprocessing. It simulates pump sensor readings, splits the data into training and test sets, then compares scaling based on statistics from all data with scaling based only on the training data. The all data version is leaky because it uses information from the test set, while the training-only version is safe. The key lesson is to split the data before calculating preprocessing statistics, so the test set remains truly unseen. Feature scaling. Scaling fundamentals. Feature scaling makes numerical variables comparable before modeling. In engineering data, different units and measurement ranges can make some features look larger even when they are not more important. Scaling puts features on a consistent numerical basis, so models are not biased by arbitrary unit choices. Feature scaling changes how measurements appear numerically without changing what they mean physically. The same shaft diameter may have different numbers in millimeters and centimeters, and different sensor values may have very different ranges, even when they are equally important. Scaling methods such as centering values, adjusting their spread, or mapping them to a fixed range help prevent units and large numerical ranges from unfairly influencing a learning model. Treat scaling as a core part of data preparation. Learn the scaling rules only from the training data, then apply the same rules to validation, test, and new data. This avoids letting future information influence training and gives a more honest estimate of model performance. Proper scaling also improves numerical stability and helps reveal issues such as outliers or faulty sensor readings. Python code, scaling fundamentals. Feature scaling adjusts numerical coordinates so that raw distances are not dominated by the units of measurement. The scaling must be learned from the training data and then applied consistently to later data. The script imports 3 key Python libraries for working with data. NumPy supports numerical calculations, Pandas helps manage and analyze tabular data, and matplotlib/pyplot is used to create visualizations. Together, these tools prepare the script for data manipulation, analysis, and plotting. We create a Pandas data frame to organize pump measurements in a structured way. It stores flow rate, pressure, and vibration values for each pump, allowing different measurement units to be handled together in one table. We split the data into a training set and a test set, using the first 4 rows for training and the remaining rows for testing. Scaling values are calculated only from the training data, then applied consistently to both sets. This prevents the test data from influencing the transformation and supports a fair model evaluation. To standardize the training data, we first find the mean of each feature to center the values. Then we calculate each feature's standard deviation using 0 degrees of freedom to measure its spread. These statistics let us scale features so they contribute more equally, even if they originally used different units or ranges. We standardize both the training and test data using the scaling values learned from the training set. Each feature is centered by subtracting the training mean and scaled by dividing by the training standard deviation. This puts both datasets on the same scale, supporting consistent model training and evaluation. After scaling, verify that the training and test data still have the same number of rows and columns as their original versions. This confirms that scaling changed only the values, not the structure, so the transformed data can be used consistently and correctly. We compare two training rows by measuring the Euclidean distance between them, first using the original data and then using the scaled data. The raw distance reflects differences in the original units, while the scaled distance reflects differences in standardized units. This shows how scaling can change the perceived distance between data points. This process gives a quick summary of the data and the effect of scaling. It reports the sizes of the training and test sets, compares the raw and scaled Euclidean distance between two pump measurements, and then summarizes the scaled training features by their rounded means and standard deviations. We create a matplotlib figure with two side-by-side plots to compare the data before and after scaling. The wide layout makes it easier to see how scaling changes the feature ranges in one view. The code creates a box plot of the training data to show how each feature is distributed in its original units. This makes it easier to see how different measurement units can lead to large differences in scale. The plot is placed on the first subplot, with the y-axis labeled to show that the values are unscaled. The code creates a box plot of the scaled training features to compare their ranges after standardization. It labels the plot clearly and uses standardized units on the y-axis, showing that the features have been transformed to make them easier to compare. To keep x-axis labels readable, rotate them slightly on each plot axis. A 25-degree rotation helps prevent label overlap and makes the visualization clearer. Adjusting the layout makes the subplots fit cleanly within the figure and prevents overlap, improving readability. Displaying the plot then shows the figure so you can compare the raw and scaled feature ranges side by side. This script shows how feature scaling makes pump measurements with different units easier to compare. It uses the training data to compute the mean and standard deviation, then standardizes both training and test data, so each feature is centered around 0 with a standard deviation of 1. The output compares raw and scaled distances between points, showing how scaling changes distance-based calculations. Box plots also illustrate how standardization reduces differences caused mainly by unit size. Scaling model effects. Scaling helps a model compare numerical features fairly when they use different units, such as temperature in Celsius and pressure in kilopascals. Without scaling, features with larger values can dominate learning and appear more important than they really are. Scaling puts features on a similar range so the model can focus on meaningful patterns rather than unit size. Scaling is essential in distance-based models because these models compare observations by how close they are. Without scaling, large number features can dominate smaller scale ones and create misleading similarities. Scaling lets features contribute more fairly, helping the model find meaningful patterns for clustering, anomaly detection, or health classification. It doesn't make every feature equally important, but it prevents numerical size from being mistaken for significance. Scaling helps gradient-based models learn efficiently by putting features on comparable ranges. Without it, features with very different scales can cause uneven updates, making training slower or less stable. Scaling creates a smoother learning process, so methods like regression and neural networks converge more reliably on diverse engineering datasets. Python code scaling model effects. Scaling can change how a model behaves because features with larger units may dominate distance calculations. By putting features on a comparable scale, the model can learn more balanced patterns and often achieve better gradient behavior during training. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting tools to create visualizations that help compare data and understand how scaling affects model behavior. We create two NumPy arrays to represent mechanical sensor features, temperature readings in Celsius and pressure readings in kilopascals. Both arrays store their values as floating point numbers and will be used for later analysis. Temperature and pressure data are combined into one two-dimensional array, with each row representing one observation and each column representing a feature. A column stacking function is used to align the two datasets side by side. Finally, the array's shape is checked to confirm it contains 4 observations and 2 features, so it is ready for further analysis. A new pump observation is created with 2 values, temperature in Celsius and pressure in kilopascals. An assertion then checks that this observation has the same number of features as the existing dataset, ensuring it matches the required dimensionality. To find the most similar existing observation, compare the new observation with each raw data point using temperature and pressure. For each one, calculate the Euclidean distance, which measures the straight-line difference across those features. The observation with the smallest distance is the closest match to the new observation. To prepare the data for scaling, we find the average value of each feature, such as temperature and pressure, and use it to center the data. We also calculate each feature's standard deviation to measure how spread out its values are. If any standard deviation is 0, we replace it with 1, so scaling remains stable and avoids division errors. The sensor data is standardized by subtracting each feature's mean and dividing by its standard deviation, so all features are on a comparable scale. The same scaling is applied to the new observation, and then differences are computed between it and each scaled training observation. This prepares the data for distance or similarity analysis. We compute the distance from the new scaled observation to each scaled observation by comparing their feature values. These distances show how similar each observation is to the new one. The observation with the smallest distance is identified as the closest match after scaling. We compare raw and scaled data by measuring the average absolute size of each feature. This shows the typical gradient magnitude before and after scaling. The comparison helps reveal how scaling changes step sizes in gradient-based optimization, which can support more stable and efficient learning. We compare the nearest machine before and after scaling, then summarize how scaling changes the distance values. This includes printing the distance range for both raw and scaled data, rounded to 2 decimal places, and comparing the average feature magnitudes in each version. Together, these outputs show how scaling affects distances and feature sizes in the dataset. We label the machines from M0 to M3, so each bar can be identified in the plot. Then we use NumPy's arrange function to create the x-axis positions for those labels. Finally, we set a bar width of 0.35, so the raw and scaled distance bars can appear side by side clearly. A bar chart is created to compare raw and scaled distances. The raw distance bars are placed slightly to the left of each category, while the scaled distance bars are placed slightly to the right. This side-by-side layout makes it easy to see how scaling changes the distances between observations. The plot is finalized by labeling the bars, marking the y-axis as the distance to the new pump, and adding a title about how scaling affects distance-based similarity. A legend distinguishes the raw and scaled data, making the comparison easier to understand. To finish the visualization, we use Matplotlib's tight layout function to keep plot elements from overlapping, then display the plot with the show function. This makes it easier to compare distances before and after scaling, and see how scaling changes similarity measures between the new observation and the existing data points. This script shows how feature scaling changes distance-based comparisons and gradient behavior. It first finds the nearest data point using raw temperature and pressure values, then repeats the calculation after centering and normalizing the features. Because scaling changes how much each feature influences distance, the nearest neighbor can change. The script also shows that scaling makes gradient magnitudes more balanced, and it summarizes the effect with distance ranges, nearest point indices, average feature magnitudes, and a comparison chart. Scaling model effects. Scaling helps a model compare numerical features fairly when they use different units or ranges. In mechanical engineering data, values like temperature, pressure, vibration, speed, and age can differ greatly in size. Without scaling, a model may overemphasize larger numbers simply because of their scale. Scaling reduces this bias, so the model can focus on real patterns in the data. Scaling is important for distance-based models because features with larger numeric ranges can otherwise dominate distance calculations. For example, motor speed might outweigh vibration level when comparing pump conditions, causing the model to miss signs of wear. Scaling helps each feature contribute more fairly, improving clustering, similarity measures, and nearest neighbor decisions. Scaling helps gradient-based models train more stably and efficiently by putting features on comparable ranges. Without it, parameters tied to large-scale features may change too quickly while others lag, making optimization slower and more sensitive to learning settings. Scaling does not add information or improve weak features, but it balances training and is an important pre-processing step in engineering workflows. Python code. Scaling model effects. Scaling can change how models behave on engineering datasets. By comparing raw and scaled distances, this example shows why scaling matters and how it can make gradient descent smoother. We begin by importing NumPy for numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the basic tools needed to compute results and display them graphically. We create two small NumPy arrays to store pump data, one for rotational speed in revolutions per minute, and one for vibration level in millimeters per second. Each array contains 4 floating point values, which keeps the data precise and ready for later numerical calculations. The speed and vibration measurements are combined into a design matrix, with each row representing one pump record, and each column representing one feature. A shape check confirms the matrix has 4 records and 2 features, so the data is organized correctly for analysis. The standard scale function standardizes a matrix by working column by column. It subtracts each column's mean to center the data, then divides by that column's standard deviation to scale it. The result is a matrix whose features have mean 0 and standard deviation 1, which helps many machine learning algorithms perform better. The raw feature matrix is standardized, so each feature has a mean of 0 and a standard deviation of 1, making the features easier to compare numerically. The scaled result is then checked to confirm that all values are finite and that no invalid numbers were introduced. The function measures how far each pump is from the first pump in feature space. It compares every other row with the first row, then calculates the Euclidean distance from those differences. The result is a vector showing each pump's distance from the first one. We compare the first pump with the others by calculating Euclidean distances from their feature differences. This is done once using the raw data and again using standardized data with mean 0 and standard deviation 1. Comparing the two results shows how scaling changes distances and prevents features with larger units from dominating the measurement. The setup defines 4 target values for a gradient descent demonstration, then prepares 2 design matrices, one using the raw features and one using the scaled features. Each matrix includes an added column of 1s to represent the bias or intercept term. This makes both versions ready for gradient descent so their behavior can be compared. This gradient descent function for linear regression starts with all weights set to 0 and tracks the loss at each iteration. In each step, it predicts values, measures the errors, records the mean squared error, and computes the gradient from the design matrix and errors. The weights are then adjusted using the learning rate, and the function returns the loss history to show how the error changes over time. We compare gradient descent on raw and scaled features by tracking the loss in each case. Raw features require a very small learning rate and can make optimization slow or unstable. Scaled features allow a much larger learning rate, leading to more efficient and stable learning. This shows why feature scaling is important for gradient descent. The code compares raw and scaled distances from the first pump, rounding the results for readability. It also reports the starting and ending loss values for both raw and scaled data to show how gradient descent changes during optimization. The key point is that scaling helps prevent large unit features from dominating distance calculations, leading to more balanced model behavior. This plot compares gradient descent using raw features versus scaled features. It shows mean squared error over each optimization step, with separate lines for the two cases. The goal is to make clear that scaling features helps gradient descent reduce error more smoothly and makes the optimization behavior easier to compare. This example shows why feature scaling matters in machine learning, especially when engineering measurements use very different units. Pump speed and vibration data are scaled, so their values are comparable, which changes distance calculations and prevents one feature from dominating. The script then compares gradient descent for linear regression on raw versus scaled data, showing that scaled data converges more smoothly and efficiently. Overall, scaling makes both distance-based analysis and optimization more stable and reliable. In this lecture, you learned to extract practical features from tabular, temporal, and image-style mechanical engineering data, implement manual train and test splitting without using machine learning libraries, and scale numerical features and explain why scaling affects distance-based and gradient-based models. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.